Hello everyone, in this video we're going to cover the content for the Groups and Algebra module. We'll start by discussing algebras. An algebra is a ring and a vector space. Formally, an algebra A over a field K, also called a K-algebra, is a ring with addition and multiplication, and it is a vector space with scalar multiplication and the same addition as for the ring. These operators must satisfy the algebra axiom, which, informally, says that the scalars commute with everything. Before we go any further, let's give some notation for this video. Throughout the rest of the video, K always represents a field and A always represents a K-algebra. Now, the definition of an algebra motivates defining a commutative algebra, which is when the algebra is commutative as a ring. Similarly, the definition of an algebra also motivates defining the dimension of an algebra, where the dimension of A is the dimension of A as a K vector space. Now, let's describe how the definition of an algebra allows us to identify K as a subset of A. Because A is a vector space, and the identity in A is a non-zero vector, the map from K to A, given by lambda maps to lambda times the identity in A, is injective. We use this map to identify K as a subset of A, hence we usually write lambda A rather than lambda dot A. Next, let's give some examples of algebras. One simple example is that the field K is itself a one-dimensional commutative K-algebra. Also, n by n matrices with matrix addition and matrix multiplication form a K-algebra of dimension n squared. For n greater than or equal to 2, the algebra is not commutative. Often, the most useful bases for this algebra are the matrix units Eij, for I and j between 1 and n, where Eij is the matrix with 1 in the ith row and jth column, and zeros in every other entry. An example of a commutative infinite dimensional algebra is the polynomial ring K adjoin X. Also, the set of all endomorphisms of a vector space forms an algebra. Formally, if V is a K vector space, the set of all K linear maps from V to V is a K algebra, where we take multiplication to be the composition of maps, and we take addition and scalar multiplication to be computed pointwise. Now, let's discuss a way to make computations in an algebra easier. When finding the product of two arbitrary elements in an algebra, it is enough to know the products of the basis elements of the algebra, and then use the distributive laws to compute their product. For example, an easier way to multiply elements in the n by n matrices is to use the relation that Eij times Ekl is equal to Eil if j is equal to k and 0 otherwise. Now, let's define the direct product of algebras. The direct product of the K-algebras A1 to AN is the algebra with underlying space of A1 times all the way up to AN, and addition and multiplication is defined component-wise. Next, let's define an opposite algebra. The opposite algebra AOP of A has the same underlying K vector space as A, but the multiplication in AOP is given by A star B is equal to BA for A and B in A. Note that AOP OP is equal to A. Following that, another type of algebra is a division algebra. An algebra A over K is a division algebra if every non-zero element A in A is invertible, i.e. there's a B in A such that A times B is equal to the identity in A, which is equal to B times A. Note that if A is finite dimensional and AB equals the identity in A, then we automatically get that BA is equal to the identity in A. Another type of algebra is a group algebra. For a group G, we define KG to be the vector space over K with basis G. Then KG becomes a K-algebra called the group algebra by taking the product on the basis elements, i.e. the elements of G, to be given by group multiplication, and then extending this to linear combinations. The identity element of KG is the identity element of G. Also, Kg is finite dimensional if and only if G is finite, in which case the dimension of Kg is the order of the group G. The group algebra Kg is commutative if and only if the group G is abelian. Now, to define another type of algebra called the path algebra, we need to define a quiver. A quiver Q is a finite directed graph. We write Q is equal to Q0, Q1, where Q0 is the finite set of vertices and Q1 is the finite set of arrows. For an arrow alpha in Q1, its starting point is S of alpha, which is in Q0, and its endpoint is T of alpha, which is also in Q0. To define a path algebra, we also need to discuss paths. Each vertex I in Q0 has the trivial path EI of length 0, with S of EI equal to I and T of EI equal to I. A non-trivial path in Q is a sequence P equal to alpha 1 to alpha r of arrows alpha I in Q1, such that T of alpha I is equal to S of alpha I plus 1 for all I from 1 to r minus 1. The length of P is the number r of arrows in this path. The starting point of P is S of P, which is equal to S of alpha 1, and the end point of P is T of P, which is equal to T of alpha r. Also, a path P in Q is an oriented cycle if P has positive length and S of P equals T of P. Paths are read from right to left. Now we can define a path algebra. For Q a quiver, the path algebra KQ of the quiver Q over K has underlying K vector space with basis of all paths in Q, and the multiplication in KQ is defined on the basis by concatenation of paths, if possible, and extended linearly to linear combinations. More precisely, for the paths P equal to alpha 1 to alpha r and Q equal to beta 1 to beta s, in Q we have P times Q is equal to beta 1 to beta s to alpha 1 to alpha r if T of beta s is equal to S of alpha 1 and 0 otherwise. So P times EI is equal to P if I equals S of P and 0 otherwise. Similarly, EI times P is equal to P if I equals T of P and 0 otherwise. Thus EI times EI is equal to EI. The identity element of KQ is equal to the sum over all the EI. Now let's move on to defining a subalgebra. A subset B of A is a K subalgebra if first B is a K subspace of A, second B is closed under multiplication, and last the identity element of A is in B. Now let's define an ideal. We say I, a subset of A, is a left ideal of A if I with addition is a subgroup of A with addition such that AX is in I for all X in I and A in A. Similarly, I is a right ideal of A if I with addition is a subgroup of A with addition such that XA is in I for all X in I and A in A. We say I, a subset of A, is a two-sided ideal, or just an ideal, of A if it is both a left and right ideal. Here's one result for ideals. Every left or right ideal of A is a K subspace of A. Using ideals, we can define a factor algebra. More precisely, if I is a proper two-sided ideal of A, then the factor ring A over I is a K algebra called the factor algebra of A with respect to I. Now let's define an algebra homomorphism. For B, a K algebra, a map phi from A to B is a K algebra homomorphism if First, phi is a k-linear map of vector spaces. Second, phi of AB is equal to phi of A times phi of B for all A and B and A, but note that it suffices to check this on basis elements if phi is k-linear. And third, if phi of the identity element in A is equal to the identity element in B. From this, we can discuss algebra isomorphisms. The map phi from A to B is a k-algebra isomorphism if it is a bijective k-algebra homomorphism. If such an isomorphism exists, then A and B are isomorphic. The inverse of an algebra isomorphism is also an algebra isomorphism. Now we can give the isomorphism theorem for algebras. Let B be a k-algebra and let phi from A to B be a k-algebra homomorphism. Then the kernel of phi is a two-sided ideal of A, and the image of phi is a subalgebra of B. If I is an ideal of A, and I is in the kernel of phi, then we have a surjective algebra homomorphism, phi bar, from A over I to the image of phi, given by phi bar of A plus I is equal to phi of A. Also, the map phi bar is injective if and only if I is equal to the kernel of phi. Hence, phi induces an isomorphism psi from A over the kernel of phi to the image of phi, given by A plus the kernel of phi maps to phi of A. Now, let's move on to discussing results for algebras of small dimension. First, every one-dimensional k-algebra is isomorphic to K. Second, every two-dimensional k-algebra is commutative. Also, any two-dimensional algebra over the real numbers is isomorphic to precisely one of the real numbers that join x over the ideal generated by x squared, the real numbers that join x over the ideal generated by x squared minus 1, or the real numbers that join x over the ideal generated by x squared plus 1. Now we're going to move on to discuss modules, so let's define a module. Informally, modules are generalizations of vector spaces where scalars come from an algebra, or more generally, a ring. The formal definition is as such: let R be a ring with identity element 1R, then a left R module, sometimes just called an R module, is an abelian group M with addition together with a map R times M to M, sending Rm to R dot M, such that for all R and S in R, we have that these following equations hold. Now, let's give some useful results for modules. Because every A module V is a K vector space, it is often convenient to define actions on a K basis of V and then check the axioms using a basis. Similarly, to simplify the construction of A modules, or to check axioms, it usually suffices to deal with elements of a fixed K basis of A. If A equals K adjoint X, it suffices to define and check the action of X. Now, let's define a type of Kx module called V sub alpha. Let V be a K vector space. Then, for any K-linear map alpha from V to V, we can turn V into the Kx module V alpha by setting G dot V is equal to G of alpha of V for G in K adjoint X and V in V. Note that alpha to the I is the I-fold composition of maps. We can now give an important result for V sub alpha. Let V be a Kx module. Then V is equal to V alpha, where alpha from V to V is the K-linear map alpha V is equal to X dot V for V in V. Next, let's define the algebra K adjoint X over the ideal generated by F. Recall that K adjoint X is a principal ideal domain. So, ideals of K adjoint X are of the form the ideal generated by F for some polynomial f in k adjoin x. If f has positive degree, then k adjoin x over the ideal generated by f is an algebra. We can now relate V alpha and the algebra k adjoin x over the ideal generated by f. Let f be a non-constant polynomial, and let a equal k adjoin x over the ideal generated by f. Then there is a bijection between these sets of A modules and the set of kx modules V alpha such that f of alpha equals 0. Now we're going to define submodules. Let R be a ring and let M be an R module. A R submodule U of M is a subgroup U with addition which is closed under the action of R. Now we're going to define the direct sum of submodules. Let R be a ring and let M be an R module, as well as letting U1 to UT be R submodules of M. M is the direct sum of U1 to UT if, first, every element of M can be expressed as the sum of elements from the submodules Ui, and second, if the intersection of Uj with the sum over all I not equal to j of the Ui is equal to 0 for all j from 1 to t. Here is one useful result for the direct sum of submodules. For r is equal to k, every k module can be decomposed as the direct sum of one-dimensional k submodule. Now we're going to define the direct product of submodules. Let R be a ring and let Mi for I and I be modules where I is an index set. The direct product of the family Mi is the R module given by the Cartesian product of the Mi with component-wise addition and R action. Now we're going to introduce the factor module. Let R be a ring and let M be an R module, as well as letting U be a R submodule of M. The factor module of M modulo U is the R module given by the cosets of M over U with R dot M plus U equal to Rm plus U for all R in R and M in M. Now we're going to move on to defining an R module homomorphism. Let R be a ring and let M and N be R modules. A map phi from M to N is an R module homomorphism if for all M1 and M2 in M and R in R, we have that phi of M1 plus M2 is equal to phi of M1 plus phi of M2, and phi of Rm1 is equal to R times phi of M1. Then let's give some results for A module homomorphisms. First, A module homomorphisms must be k-linear. Also, it suffices to check that phi of Rm equals R of phi-m for basis elements R in A, or just for elements which generate A, such as x for A is equal to k adjoin x. Now we can define an isomorphism of R modules, which is a bijective R module homomorphism. Here is one result for isomorphisms of modules. If phi is an isomorphism of modules, then so is its inverse map. Now we can give the isomorphism theorem for modules. Let R be a ring. The first part of the theorem is that if phi from M to N is an R module homomorphism, then the kernel of phi is an R submodule of M, and the image of phi is an R submodule of N. Moreover, it says that M over the kernel of phi is isomorphic to the image of phi. The second part of the theorem is that if U and V are submodules of an R module M, then U plus V and U intersect V are R submodules of M. Moreover, U over U intersect V is isomorphic to U plus V over V as R modules. The third part of the theorem is that if U and V are submodules of an R module M, such that U is a subset of V, which is a subset of M, then V over U is an R submodule of M over U, and M over U over V over U is isomorphic to M over V as R modules. Now let's give a useful result for the pre-image for module homomorphism. Let R be a ring, and let phi from M to N be an R module homomorphism. Then, for every R submodule W of N, the pre-image is an R submodule of M, which contains the kernel of phi. Now, we're going to define some notation for the pre-image of the natural homomorphism. Let R be a ring, and let M be an R module, as well as letting U be a submodule of M with factor module M over U. The natural homomorphism is pi from M to M over U, where pi of M is M plus U. Then, for every submodule W of M over U, the pre-image under pi is a submodule of M containing U. Using this notation, we can give a useful result involving submodules and factor modules. Let R be a ring, M an R module, and U an R submodule of M. Then the map W to W hat induces an inclusion-preserving bijection between the set F of R submodules of M over U and the set F of R submodules of M that contain U. Its inverse maps V in S to V over U in F. Next, we're going to give a way of writing a module as the direct sum of an image and a kernel. Let M, N, and N' be non-zero A modules, and let J from N to M and pi from M to N' be A module homomorphisms such that pi circ J from N to N' is an isomorphism. Then J is injective and pi is surjective, and we get that M is equal to the direct sum of the image of J and the kernel of pi. Now we're going to move on to discussing representations. So to start with, let's define a representation. A representation of A over K is a K vector space V with a K algebra homomorphism theta from A to the K endomorphisms of V. Now let's describe how representations relate to modules. Informally, the representation corresponding to an A module V describes how an element A in A acts linearly on the vector space V and vice versa. Formally, if V is an A module with A action from A times V to V given by A dot V, then a representation of A is given by theta from A to the K endomorphisms of V, sending theta of A of V to A dot V for all A in A and V in V. Conversely, if theta from A to the K endomorphisms of V is a representation of A, then V becomes an A module by setting A times V to V such that A dot V is equal to theta of A of V for all A in A and V in V. Now we want to define equivalent representations. If theta 1 from A to the K endomorphisms of V1 and theta 2 from A to the K endomorphisms of V2 are representations of A, then they are equivalent if there is a vector space isomorphism psi from V1 to V2 such that theta 1 of A is equal to psi inverse of theta 2 of A of psi for all A in A. Here is an alternative definition of equivalent representations. The representations of A, theta 1 from A to the K endomorphisms of V1, and theta 2 from A to the K endomorphisms of V2 are equivalent if and only if the A modules V1 and V2 are isomorphic. Next, let's give a result for representations of factor modules. Let I be a proper two-sided ideal of A with factor algebra A over I. Then the representations of A over I are in bijection with the representations of A whose kernel contains I. The bijection takes a representation psi of a over I to the representation psi circ pi, where pi is the natural homomorphism. In terms of modules, this means that there is a bijection between the set of a over I modules and the set of a modules v for which xv equals 0 for all x in I and v in v. Now we'll move on to defining a representation of a quiver. If q equals q0 q1 is a quiver, then a representation v of q over k is a set of k vector spaces vi for I in q0 with k linear maps v alpha from vi to vj for each arrow alpha from I to j. We can write v is equal to the tuple of the vi for I in q0 and the v alpha for alpha in q1. Informally, for a quiver q, a representation of q is equivalent to a kq module. Formally, if v equaling vi v alpha is a representation of q over k, then the direct product v becomes a kq module as follows. Let v be in v, and let p from alpha 1 to alpha r be a path starting at s of p and ending at vertex t of p. Then set p dot v is equal to this thing here, where the possibly non-zero entry is in position t of p. The action is extended to all kq by linearity. Conversely, if v is a kq module, then for any vertex I in q0, we can set vi equaling eiv, and for any alpha from vertex I to vertex j, we can set v alpha from vi to vj given by e dot v is equal to alpha dot v. Then v is a representation for the quiver q over k. These two constructions are inverse to each other. Now we're going to focus on simple modules. So let's start by defining a simple module. An A module V is simple if V is non-zero and it has no A submodules other than 0 and V. Next, let's give an equivalent way of thinking about simple modules. If V is a non-zero A module, then V is simple if and only if AV equals V for all non-zero V in V. Next, let's give a result for simple factor modules. Let V be an A module, and let U not equal to V be a submodule of V. Then the factor module V over U is simple if and only if U is a maximal submodule of V. Now we're going to define the inflation of a module. Suppose I not equal to A is a two-sided ideal of A, and let B be the factor module A over I. Then any B module M can be viewed as an A module with action AM is equal to A plus IM for all M in M, which we call the inflation of M to A. Now we can use inflations to find simple A modules. Let B be A over I, where I not equal to A is an ideal of A. If S is a simple B module, then the inflation of S to A is a simple A module. Now let's move on to defining a composition series. A composition series of an A module V is a finite chain of A submodules starting at 0 and ending at V, such that the factor modules Vi over Vi minus 1 are simple for all I from 1 to n. We call these factor modules the composition factors of V. The length of the composition series is n, the number of factor modules appearing. The terms of the composition series are the Vi. Now let's discuss when modules have composition series. Not all modules have a composition series. On the other hand, every finite dimensional A module has a composition series. Also, if an A module V has a composition series, then every submodule of V also has a composition series. Now let's define equivalent composition series. In general, a module can have many composition series, even infinitely many different ones. Two composition series for the same module are called equivalent. However, the Jordan-Holder theorem shows that any two equivalent composition series have the same length and the same factors up to isomorphism and reordering. Formally, the theorem states that if an A module V has two composition series, then n equals m, and there is a permutation sigma of 1 to n such that the Vi over the Vi minus 1 are isomorphic to W sigma I over W sigma I minus 1 for all I from 1 to n. One consequence of the Jordan-Holder theorem is that the composition factors only depend on the module, not on the composition series. The proof of the Jordan-Holder theorem uses the following lemma. Using the notation from the theorem, suppose that Vn-1 does not equal Wm-1. Let D be the intersection of Vn-1 and Wm-1. Then Vn-1 over D is isomorphic to V over Wm-1, and Wm-1 over D is isomorphic to V over Vm-1, and these factor modules are simple A modules. Next, let's define the length of a module. For every A module V, the length LV is defined as the length of a composition series of V if it exists, and otherwise LV is set to infinity. An A module V is of finite length if L of V is finite, i.e. V has a composition series. Now let's give some useful results for the lengths of modules. Suppose V is an A module which has a composition series. Then for every A submodule U of V, first, the factor module V over U has a composition series. Second, there is a composition series of V where U is one of the terms, and moreover, L of V is equal to L of U plus L of V over U. Third, L of U is less than or equal to L of V, and if U does not equal V, then L of U is strictly less than L of V. Next, we'll define the annihilator of an element in a module. For V an A module and V in V, the annihilator of V in A is the set of all A in A such that AV is equal to 0. Hence, we get the following results for the annihilator. We can show that for every V in V, we have that A over the annihilator of V is isomorphic to AV as an A module. If S is a simple A module, then for every non-zero S in S, we have that S is isomorphic to A over the annihilator of S as A modules. Now, we'll move on to giving some useful results limiting the number of simple modules. If A has a composition series as an A module, then every simple A module occurs as a composition factor of A. So, there are only finitely many simple A modules up to isomorphism. Thus, if A is finite dimensional, then every simple A module is finite dimensional. Now, we'll state a theorem which describes the simple modules of quotients of the polynomial ring. If A is equal to k adjoint x over the ideal generated by f, where f has positive degree, then first, the simple A modules are, up to isomorphism, precisely the A modules k adjoint x over the ideal generated by h, where h is an irreducible polynomial dividing f. Second, writing f as a product of irreducible polynomials, which are pairwise coprime, we get that A has precisely R simple modules up to isomorphism, namely k adjoint x over the ideal generated by f1 up to k adjoint x over the ideal generated by fr. We can use this to find a composition series of the algebra A equaling k k adjoint x over the ideal generated by f as the regular A module. Let f be the product of f1 to ft with fi irreducible, but not necessarily pairwise co-prime. This gives a series of submodules of A, namely 0, I1 over the ideal generated by f, up to it-1 over the ideal generated by f, A, where ij is the ideal of k adjoint x generated by f of j plus 1 up to f of t. Then, all vector modules are simple, and hence we have found a composition series of A. Next, we're going to define some simple modules for path algebras. Let Q be a quiver without oriented cycles. Then A equaling KQ is finite dimensional. We'll label the vertices of Q by Q0 is equal to 1 to n. For vertex I in Q0, we get the A module AEI, which, as a vector space, is spanned by the paths which start at I. The A modules AEI have a submodule JI, which is AEI greater than or equal to 1, spanned by all paths of positive length, starting at vertex I. Hence, we get the one-dimensional, and thus simple, vector A modules SI equaling AEI over JI, which are the span of EI plus JI for I from 1 to n. Letting P be the set of all paths in Q, the A action on the SI is given by EI times EI plus JI is equal to EI plus JI, and P times EI plus JI is equal to 0 for all P in P not equal to EI. We can show, using a proof by contradiction, that the A modules S1 to Sn are pairwise non-isomorphic. Informally, these are the only simple K modules up to isomorphism. Formally, let Q be a quiver without oriented cycles, and let the vertices of Q be given by Q0 equaling 1 to n. Then the finite dimensional path algebra A equaling KQ has precisely the simple modules up to isomorphism given by S1 to Sn, where Si is equal to AEI over Ji for I in Q0. So all simple A modules are one-dimensional, and they are labelled by the vertices of Q. Also, we get these results for each vertex I in Q0. First, the space EIA-EI is one-dimensional and spanned by EI. Second, the only maximal submodule of AEI is JI, and also EIJI equals 0. Now, let's move on to discussing simple modules with the direct product of algebras. First, let A equal A1 times all the way up to AR be the direct product of K algebras. Then, for I from 1 to R, any simple AI module S becomes a simple A module by setting A1 to AR dot S equal to AIS for all A1 to AR in A and S in S. Letting epsilon I equal this for I from 1 to R, we get that for every A module M, first letting Mi equal epsilon IM, we get that Mi is an A submodule of M, and M is equal to the direct product of M1 up to Mr. Second, if M is a simple A module, then there is precisely one I from 1 to R, such that Mi is not equal to 0, and this Mi is a simple A module. We can now completely describe all simple modules for a direct product. Formally, for A equaling A1 times all the way up to AR, a direct product of K algebras, these simple A modules are precisely the inflations of the simple AI modules for I from 1 to R. Now, let's move on to giving Schur's lemma. Suppose S and T are simple A modules, and phi from S to T is an A module homomorphism. Then, first, either phi is equal to the 0 map, or phi is an isomorphism. So, for every simple A module S, the endomorphism algebra is a division algebra. Second, if S equals T, and they are finite dimensional algebras over the complex numbers, then phi equals lambda times the identity function for some lambda in the complex numbers. Now, let's move on to defining the center of an algebra. The center of A is the set of all elements of A which commute in A. Then, by applying Schur's lemma, we get the following result. If A is an algebra over the complex numbers, and S is a finite dimensional simple A module, then for all Z in the center of A, there is some lambda Z in the complex numbers such that Zs is equal to lambda Zs for all S in S. Hence, we get the following corollary for commutative algebras over the complex numbers. If A is a commutative algebra over the complex numbers, then every finite dimensional simple A module is one-dimensional. Now, let's move on to discuss semi-simple modules. First, let's define a semi-simple module. A non-zero A module V is semi-simple if it is the direct product of simple submodules, i.e. there exist simple submodules Si for I in some index set I, such that V is equal to the direct sum over all the Si. Now, let's define a cyclic module. For R a ring, an R module M is cyclic if there exists an M in M such that M is equal to Rm, i.e. M is generated by a single element. We have the following result for cyclic modules. If M is a non-zero cyclic R module, then M has a maximal submodule and hence has a simple factor module. We also have this lemma for submodules. If V is an A module such that every submodule U of V has a complement, then every non-zero submodule of V has a simple submodule. Using this, we can prove the following theorem, which describes equivalent ways to define a semi-simple module. If V is a non-zero A module, the following statements are equivalent. First, for every A submodule U of V, there exists an A submodule C of V called the complement to U in V, such that V is equal to the direct sum of U and C. So for all U, a submodule of V, we have that U is isomorphic to V over C, and V over U is isomorphic to C. Second, V is the direct sum of simple modules, i.e. V is simple. And third, V is a sum of simple submodules. Now, let's discuss some corollaries to these equivalences. First, if phi from S to V is an A module homomorphism, where S is a simple module, then phi is equal to 0, or the image of phi is a simple A module isomorphic to S. Second, if phi from V to W is an isomorphism of A modules, then V is semi-simple if and only if W is semi-simple. Third, all non-zero submodules and all non-zero factor modules of semi-simple A modules are semi-simple. Fourth, if Vi are a family of non-zero A modules, then the direct sum of the Vi is a simple A module if and only if all Vi are semi-simple A modules for I in I. Now, we're going to move on to discuss semi-simple algebras. So, let's define a semi-simple algebra. We say A is a semi-simple algebra if A is semi-simple as the regular A module. Now, let's give some remarks for semi-simple algebras. First, a semi-simple algebra has finite length as an A module. Second, every simple A module is isomorphic to one of the modules which appear in the direct sum decomposition of A. Now, let's give an equivalent definition of a semi-simple algebra. We have that A is a semi-simple algebra if and only if every non-zero A module is semi-simple. Following this, we get the following corollary relating simple algebras to algebra homomorphisms. If B is a K-algebra, then First, if phi from A to B is a surjective homomorphism and A is a semi-simple algebra, then so is B. Second, if A and B are isomorphic, then A is semi-simple if and only if B is semi-simple. Third, every factor algebra of a semi-simple algebra is semi-simple. Now, let's discuss when the quotient of the polynomial ring is a semi-simple algebra. Let f be a non-constant polynomial with factorization into irreducible polynomials given by this expression here, with the f1 up to fr pairwise co-prime. Then k adjoint x over the ideal generated by f is semi-simple if and only if the ai are equal to 1 for all I from 1 to r, i.e. f can be written as f1 times fr, the product of pairwise co-prime irreducible polynomials. Next, let's discuss when factor modules are semi-simple. If I is a subset of A, which is a two-sided ideal of A, with I not equal to A, and if B equals A over I, the factor algebra, then for any B module V, we have that V is a semi-simple B module if and only if V is a semi-simple A module with IV equal to 0. Then we can determine when a direct product is a semi-simple algebra. For A1 up to AR K algebras, the direct product of the A1 up to AR is a semi-simple algebra if and only if AI is a simple algebra for all I from 1 to R. Now let's give some results for division algebras. First, if D is a division algebra over K, then for all n in the natural numbers, the matrix algebra of the n by n matrices is a semi-simple K algebra. Second, for D1 up to DR division algebras over K and N1 up to NR natural numbers, the direct product of the N1 by N1 matrices up to the NR by NR matrices is a semi-simple K algebra. This proves one direction of the Artin-Wedderburn theorem, which states that if A is a semi-simple algebra, then there exists positive integers R and N1 up to NR, and division algebras D1 up to DR over K, such that A is isomorphic to the N1 by N1 matrices over D1 times all the way up to the NR by NR matrices over DR. Conversely, every K algebra of the form given here is semi-simple. And, as always, thank you for watching.